Creative video presentation about LED.
Hello, my name is Jeiel in BT Electrical 2A. I will discuss about LED. A light emitting diode, or LED, is an optical semiconductor device that emits light when voltage is applied by converting electrical energy to light energy.
History and development of LED or light-emitting diode. Early discoveries. In 1907, British experimenter H.J. Round of Marconi Labs observed electroluminescence while working with silicon carbide crystals. In 1927, Russian inventor Oleg Lusev published a paper detailing his research on electroluminescence in silicon carbide diodes, though no practical LED was created at that time. So let's dive into the different parts and functions of a LED. Let's begin to the epoxy dome lens. It serves multiple crucial roles in an LED, like light transmission, light focusing, and protection. Light transmission. It allows most of the light generated by the semiconductor to escape the LED package. Light focusing. It shapes the light beam, determining the viewing angle of the LED. This can be narrow for focused applications or wide for broader illumination. Protection. It acts as a protective barrier, shielding the delicate semiconductor from external elements like dust, moisture, and physical damage. Number 2 is the lead frame. The lead frame is a metal structure that provides mechanical support and electrical connections for the LED chip. It holds the LED chip in place, ensuring stability and preventing damage during the assembly process. Also, it provides a pathway for electrical current to flow between the LED chip and the external circuitry. Lastly, it can help dissipate heat away from the LED chip, improving its performance and lifespan. Number 3 is anode, which is positive, and cathode, which is negative. The anode and cathode are the two terminals of the LED. Anode is the positive terminal where electrical current enters the LED. Cathode is the negative terminal where electrical current exits the LED. Correctly identifying and connecting the anode and cathode is crucial for the LED to function properly. Bonding wire. The bonding wire, usually made of gold or copper, connects the LED chip to the lead frame. It provides a conductive pathway for current to flow between the chip and the lead frame, enabling the LED to light up. It can help dissipate heat generated by the LED chip, and the quality and type of bonding wire directly impact the LED's reliability and lifespan. Phosphor. The phosphor is a material that converts the light emitted by the LED chip into a different color or white light. Phosphor absorbs high-energy light from the LED chip and re-emits it at a longer wavelength, changing the color of the light. In white LEDs, a blue LED chip is combined with a yellow phosphor to create a white light spectrum. The choice of phosphor influences the color rendering index, or the CRI, of the LED, determining how accurately it reproduces colors. Light waves. Light waves are the electromagnetic radiation emitted by the LED. LEDs emit light in the visible spectrum, which allows us to see them. This is an example of visible light. Light waves are a form of electromagnetic radiation traveling at the speed of light. The wavelength of the light emitted by an LED determines its color. Light-emitting diode. The light-emitting diode, LED, itself is the core component of the LED package. It emits light when an electrical current passes through it, a phenomenon known as electroluminescence. It's made of a semiconductor material that allows for the flow of electrons and holes, leading to the emission of light. The energy band gap of the semiconductor material determines the color of the light emitted. Lastly is the reflector cup. The reflector cup is a component that directs and shapes the light emitted by the LED. It reflects light emitted by the LED, focusing it in a specific direction. It can improve the efficiency of the LED by maximizing the amount of light that reaches the intended target. So let's move to the different layers of an LED. We're going to delve into the fascinating world of light-emitting diodes, or LEDs. These tiny devices have revolutionized lighting and display technology, and understanding their inner workings is key to appreciating their capabilities. At the heart of an LED lies a special type of material called a semiconductor. Specifically, LEDs utilize a p-type semiconductor. This material is created by introducing impurities, like boron, into a pure semiconductor like silicon. These impurities create holes in the crystal lattice, which act as positive charge carriers. Now that we've explored the p-type semiconductor and its holes, let's shift our attention to its counterpart, the n-type semiconductor. While the p-type is characterized by a surplus of holes, the n-type is defined by an abundance of free electrons. This abundance of free electrons within the n-type semiconductor is what gives it its name, N, for negative. It's these electrons that will play a crucial role in the recombination process that ultimately leads to light emission in an LED. Let's proceed to the active region. The active region is the middle of the bridge, where the two sides come together and interact. Imagine a busy city street where people are constantly moving. The active region in an LED is like a specific intersection where people from both sides of the street meet and exchange information. This exchange is what generates the light in an LED. The active region in an LED is not something you can physically see. It's a process that happens within the semiconductor material. While p-n junction is the interface. I use interface word as a p-n junction because this is a general term for a boundary between two charge carriers, like a wall, but it also implies a point of interaction. It can be a barrier that prevents charge carriers from combining, but also a place where they can interact. The two charge carriers that I was said are the holes and free electrons. Last part is the substrate. The substrate in an LED chip, it serves several important purposes like structural support. The substrate provides a solid foundation for the entire LED structure. It's usually made of a material like silicon or sapphire, which is strong and stable. This allows for the fabrication of the LED chip and its packaging without deforming or breaking. The substrate acts as a path for electrical current to flow. It's typically made of a material with a high electrical conductivity, allowing for efficient current flow to the active region of the LED where light is generated. Overall, the substrate in an LED chip is a critical component that provides structural support, electrical conductivity, heat dissipation, a platform for epitaxial growth, and sometimes optical properties that enhance light output. And now let's discuss about depletion region. The depletion region is the area near the p-n junction where there are very few free charge carriers. This region is formed due to the diffusion of charge carriers across the junction, creating an electric field that prevents further diffusion. Depletion region. The depletion region is the area near the p-n junction where there are very few free charge carriers. This region is formed due to the diffusion of charge carriers across the junction, creating an electric field that prevents further diffusion. Imagine the wall has a gap or a depletion region in the middle. This is where the electric field exists, repelling electrons and holes from both sides, making it difficult for them to cross. That was the example of depletion region. So let's proceed to recombination or recombination process. Recombination process in LEDs is the process where an electron in the conduction band recombines with a hole in the valence band, releasing energy in the form of a photon, which is emitted as light. That's all for this video. Thank you for watching and completing my creative video presentation about LED.